Go ahead, Mauricio.
Okay, welcome everyone for this edition of a Brazilian Algebraic Geometry Seminar. Today we have Alan Muniz. It's a pleasure to introduce him. He's going to talk about one moduli space of a rank 2 logarithmic connections over an elliptic curve. Go ahead, Alan, please.
Thank you, Mauricio. Thank you, all the organizers for the invitation. It's a pleasure to speak here. So I'm going today. It's a project still in progress, but with Thiago Fassarella and Frank Loray, and we are going to describe some modular spaces of logarithmic connections. In this case, the connections over an elliptic curve. So first, we fix a curve, a curve C, smooth and project over the complex numbers. And if you are giving a vector bundle or a locally free chip, I will actually use both. Both are the same for us, as usual. Well, we have a vector bundle over C. Then we define a logarithmic connection by a C-linear map that takes a section of E and gives you a differential form with values on E. But this differential form, as the logarithmic name says, it has some poles, but they are all simple. And that's all. See that this map is C-linear, but it satisfies Leibniz rule, but that's important. And don't know if somebody's not used to this stuff, but these are primarily analytic objects, but we will see that their modular space is an algebraic variety. Well, in this setting. So locally a connection, we can write that a trivialization for the bundle. So a section have some components, and the connection just takes these local functions and spits out the derivatives plus some matrix applied on these functions. This matrix, obviously, from the definition, its entries are some differential forms with simple poles on the divisor that we have fixed. We define for a connection some residuals at each pole, at each point on the spot of D. Then we define the residual by the residual of the matrix A. Here we are talking about a matrix whose every entry is the residual of the form on the matrix A. So this is well defined. So if we fix some trivialization, we have the matrix A, but if we change the trivialization, we only change coordinates here. So this is a well-defined element of the endomorphism group. Endomorphism of this fiber of the vector bundle. Here we are talking about, here we are talking about the fiber of the vector bundle, not the stalk of the sheaf. That's to be clear. Well, Some cases are known. For instance, if we take the curve to be P1 and the divisor is degree 3, then we have 3 poles. The moduli space has exactly 1 point. This, which corresponds to the Gauss geometric equation with some fixed parameters. If we change the data that we use to define the modular space, we change the parameters of the hypergeometric equation. But for n bigger or equal to 4, these modular spaces will be what's so-called the Okamoto spaces of initial conditions for the Garnier systems. These are very well described. We have some recent work that shows that these spaces are actually some component of the Hilbert scheme of points on. Sorry, it's the actual Hilbert scheme of points of some Hirzebruch surface, and all the data to form the surface and the number of points and the position of these points is related to the data that we need to define the space. Well, moving to genus 1, with 1 pole, it is equivalent to the case when C equals to P1 and N equals. Here, the thing is to have a connection with 1 pole. This pole will be invariant by the hyperelliptic involution, and everything descends to P1, and have the case with 4 poles. When G equals to 1 and we have 2 poles, this is the case that was described by Thiago and Frank in 2018. And the aim of this work is to generalize this work for an arbitrary number of poles. Here we are going to describe in the same fashion of this work the case where n is greater than 2. Actually, the case n equal to 2 will be included. So we fix the data that we want is an elliptic curve. It's already polarized. W is a point that will be the identity of the group structure. A general reduced divisor with any points. By general here, we mean that when you see these points in the group structure of C, these points are not two torsion. As if you multiply, take the square of 1 point of any of these points, it cannot be equivalent to W. We fix a trace connection. Here we are going to fix a line bundle and a connection on this line bundle. Also logarithmic with respect to this divisor. and we fix some eigenvalues. Here we have described the connection have some poles and some residuals. Each residual will have two eigenvalues that are going to be fixed. And define, with all this data fixed, we can define the modular space as a GIT quotient. You take the pairs of vector bundles of rank 2 on C, connections, the logarithmic with respect to D, with fixed trace, fixed spectrum, and here we take the semi-stable locus and mod out by S equivalence. Well, I'm not going to enter in some detail how this is formed, but because in our case, if these eigenvalues are generic enough, we can see that this modular space is a smooth quasi-projective variety of dimension 2n. The trick here is that for generic eigenvalues, every object here does not have sub-objects, so everything is stable. And then we have come to the results that I want to explain you today. Well, the genericity condition that I'm assuming is this one, that the sum of the eigenvalues taking either the plus or the minus eigenvalue, this cannot be an integer, and the difference between two eigenvalues of the same residual cannot be 0, 1, or minus 1 for any k. This is the conditions that we are assuming that these eigenvalues satisfy. So we can describe the whole modular space as a sigma n plus a union of a bunch of spaces that I hope you will be familiar at the end of the talk. And these ranges in some set, and well, and the one point is that each piece here is isomorphic to Sn where S is P1 cross P1 minus the diagonal. So these pieces that we are putting together are very easily described. These spaces that we can describe on isomorphism with this variety that is really easy to understand, and we can describe our modular space. There's a bit hard to know what it is by some gluing of these things, plus some other stuff that poses some difficulty to understand. But I like to point out that if the number of poles is even, this space is empty. Later, I try to explain to you what this thing is and why it's empty when the number of poles is even. Well, and
Alan, can I ask a question?
sure.
So is this a moduli space, is it irreducible?
Yes, yes, I forgot to mention that.
Okay,
It's it's a smooth cross-projective irreducible.
okay, thank you.
So the theorem that I want to show you is that after the description of the space as a union of subspaces that are easily described, we actually show that outside this sigma n, we can define this space as a gluing actually of many copies of this SN. And this gluing satisfies some well-behaved, it's well-behaved, but you have a birational map between a birational automorphism of SN, you can say, that is fiber preserving. This map preserves some projections to P1 to the n. Recall, S is P1 cross P1 minus the diagonal. We have one projection that goes to P1, and we have some projections that from Sn to P1 to the nth power, and S to the nth power to P1 n power, and this diagram commutes. And this is birational, but it is well defined. It is as an isomorphism outside the the pre-image of a divisor here in P1 to the n power. In this divisor, we can show that the degree was d1 to dn, and dj is true if j is in this set I that I'm using here to parameterize, and dj is otherwise. So let's get into the ideas behind these results. First, I have to talk to about quasi-parabolic vector bundles. Well, we have a curve and a divisor, reduced divisor. A quasi-parabolic vector bundle is a pair of a vector bundle and some P that are a collection of subspaces of the fibers of the vector bundle at the points of this divisor. Well, this is a rather a simplification to the case that E has rank 2, but it comes from a very general theory, and that for each point of the divisor, we put a flag of subspaces on the fiber of the vector bundle. So, but as we are in rank 2, we only care about defining a subspace of dimension 1, actually. We only care to define a direction on the fiber of E at Tj for j from 1 to n. Well, for this kind of object, we define some stability condition that say that for each line subbundle of E, we take n real numbers from between 0 and 1, and define this stability condition that, well, it's the degree of E minus 2 times the degree of L plus some weighted sum, signed sum of weights, depending on if the directions that have fixed, the parabolic directions, are contained in the line bundle or not contained in the line bundle. Well, for those that are familiar with this theory of parabolic bundles, here we have a notion of parabolic degree, and this condition is just the difference of the parabolic degree of E minus, it's the parabolic degree of E minus the parabolic degree of L. So with this number in hand, we say that a quasi-parabolic vector bundle is mu semi-stable if we have the usual inequality. And we can define the modular space of quasi-parabolic connection, quasi-parabolic vector bundles, sorry, with fixed determinant. Well, as one would expect, with this set of weights, it have a chamber decomposition, have some walls and some chambers. We have a special, some very good chamber that is given by the sum of the weights is less than 1. This is very special since for every weight in this chamber, we have the modular space of semi-stable semi-stable parabolic bundles is just the quasi-parabolic structures on E1. That's the unique non-trivial extension of OW by O. This, well, as the weight is inside the chamber, so everything is here. Everything is stable, and we have this very nice property that in this chamber, the vector bundle, the underlying vector bundle, is fixed. We only have to change the P, the directions. Of course, this vector bundle does not have automorphism, so we have exactly does not have non-trivial automorphism actually. So we have exactly one object for. We give the directions. We have a structure. We have a point in this modular space. And so if we can show that we only have to give the directions, so this, well, with a bit of work, we can prove that this is actually an isomorphism. The modular space in P1 cross P1 n times. Each P1 accounts for one direction here. So what we can do for the other chambers? For the other chambers, well, not all other chambers, but we can see that we have a map of this open hypercube that exchange weights in this fashion have for given a subset of this set of 1, 2, and we maintain the weights that are not online and change the weight. We take the weight and change it to 1 minus that weight. And this map, we can show that this map preserves the chamber decomposition. And we are going to denote by Ci the image of that first chamber by this map. And we denote by xi the corresponding moduli space. So we saw that we have a very special moduli space for when the weights lie on this first chamber. And what we are going to show is that not for all weights, but for most weights in that from, well, not always most weights, but these weights that we can achieve by these maps, the moduli space is good also. The point is that this map Psi admits a modular realization. We can define a map between moduli spaces. That's actually an isomorphism of moduli spaces that's given by elementary transformations. In particular, for each I, say this a set of even cardinality, we have that this space is also isomorphic to a power of P1. Well, just to point out what is this map that we are considering and why we require this subset I to be of even cardinality. But in the case of this I has even cardinality, we see that we can take the subdivisor of D, where the sum of Ti, where I lies in the set I, and since this number is even, we can take the square root of this line bundle, and for this fixed square root, we can define a map. First, we consider a skyscraper sheaf supported on the Ti, where I lives in I, in capital I, and we take the evaluation map. Here we just take we take a section of E, takes its values on these points, mod out by Pi, and see well, this what we achieve here. And the kernel of this map is a locally free sheaf that consequently is a vector bundle as well. And so note that this map here is a map of locally free sheaves, but not of vector bundles. Well, but this vector bundle is well defined, and we can twist by this L naught, and we have a vector bundle that has the same determinant as E. So we are in the same setting for the moduli space. So we can talk to send the moduli space of the first chamber for for a moduli space of the other chamber. The new quasi-parabolic structure is well determined by this map alpha. Well, this say in a few words, if the point in the spot of D that's not correspond to an index here in I, then we just pull back the direction by alpha. That alpha is an isomorphism of vector bundles. Well, and when the point is here, we can define in another way what these directions will be. Well, so why did I spend some, say, 10 minutes for talking about this quasi-parabolic vector bundles? The point is that for any connection, well, recall that for a connection has some residues, and these residues have some semi-eigenvalues and some eigenvectors. So we can take these eigenspaces to define underlying quasi-parabolic structures on E. So we recall the eigenvalues are nu plus or nu minus in each point. Here, just the k should have been down there, but we fix some epsilon that just a combination of plus or minus signs, and we take the respective directions given by nabla, and we define this quasi-parabolic structure. And the point is, when we are looking to the whole moduli space, we restrict ourselves to the connections that have some underlying quasi-parabolic structure that is stable for some weight. So we define this space that is, we take all the connections that when we take the epsilon directions, the underlying quasi-parabolic vector bundle is mu stable for a weight in the chamber Ci. So that's a bunch of subspaces like that, and for epsilon and I varying wherever they can. Well, it turns out that these smaller, well, have seen from the statement of the theorem that these subspaces are very neat, very easily described, at least when we assume some genericity for the eigenvalues nu. And that's our proposition here. Recall that for the first chamber, that the ones that the sum of the weights are less than 1, we can see that if the underlying quasi-parabolic vector bundle is mu stable for a mu in this chamber, then the underlying vector bundle is E1. And this is everything. This subspace is just the connections with a fixed vector bundle. And this is the most simple thing that we may get. We have a fixed. We don't have to deform the vector bundle alongside the connection. We only have to deform the connection. So if we assume that the difference of the eigenvalues in each pole is not 0, we can prove that this map is an isomorphism. That is, we take the connection and take a connection and give all the eigenspaces. Here we need this assumption just for these directions be actually well defined, since if we have equal eigenvalues, we don't have distinct, well defined eigenspaces. And recall that here S is P1 cross P1 minus the diagonal. Well, as I told you some minutes ago, that we have an isomorphism between these moduli spaces of quasi-parabolic vector bundles, and one may expect that we have a corresponding isomorphism between these moduli spaces. But this is almost true, and the only thing that happens is that the spectra change. And we have this result that says that isomorphism corresponds to an isomorphism between these spaces of connections, but here the eigenvalues are different. And here we can see how they transform, and this map phi I is just it is just the pullback of the connection by this map. Say when we have defined the elementary transformation, we have a map from E prime to E, and that map alpha, we can use that map alpha to pull back the connection, and then twist the connection with a connection in for the line bundle L0, and this gives a connection here. And the thing here is that the quasi-parabolic bundles agree when you take the pullback of the connection. the direction it has is the epsilon directions it has correspond to the directions that are defined by this map downstairs, and everything here commutes. Well, we have that this space with good eigenvalues is isomorphic to S to the n power. So if lambda is good enough, we have the same isomorphisms. So we have the isomorphism if the difference between the nu is not equal to one of these numbers, -1, 0, or 1. Here comes that our second or third assumption on these eigenvalues. So we are back in the main results, or the main results. So we have seen that we take these assumptions so that the whole moduli space is smooth, irreducible, quasi-projective. We take these assumptions so that each piece here is an S to the nth power, and that's all. Yeah. And we have this setting. I have not told you about this thing yet. Yeah. That's the next thing that I want to show you. The point here is that we have taken the subspaces where the underlying quasi-parabolic vector bundle is stable for some weight. But this is not always the case. And here it's where it comes the sigma n. Well, to see that, what we have actually for each underlying quasi-parabolic bundle is that it is always indecomposable. If it is, and we classify the quasi-parabolic vector bundles that are indecomposable. So if the underlying vector bundle is actually indecomposable, then from the determinant, we see that the only possibility is E1. We can have a quasi-parabolic structure that does not decompose, but the underlying vector bundle is decomposable. And we have these two possibilities. Either the degree of L, well, the double of it, 2 times the degree of L, is less than or equal to n, or it is equal to n plus 1. And we have some special position for the quasi-parabolic directions. So if the connection, we have a connection here, the underlying vector bundle is E1, it's indecomposable, we have that every underlying quasi-parabolic structure is stable for weights in that first chamber. So, well, this connection lies here in this space. if it's decomposable, but 2 times the degree of L is less than or equal to n, we can give some argument here to choose, can choose very well the epsilon. We can choose the directions, and this I such that have some conditions. Have the cardinality of is 2 times the degree of L. Well, we can do that since 2 times the degree of L is less than or equal to n. And we have some intersection here. The idea here is that when you consider this situation, when we can compute the stability condition for any subbundle of this bundle, and see that this underlying quasi-parabolic vector bundle is stable. And the last case, when 2 times the degree of L is n plus 1, we define this guy here, this space. There's something that we can describe better this space, but the point is that this is precisely the connections over a square root of I missed the original d plus w. W is the well that we use to polarize the curve. And we take a square root, and well, n is odd. This number is even. We take a square root of this line bundle, and we have all the connections here for this line bundle. In particular, here we see that clear that if n is even, this cannot happen, and the sigma n is empty. So, the moduli space is covered by these subspaces. It's really simple, but in the odd case, so in the even case, only these two situations happen. But in the odd case, that we have this awkward piece of the moduli space. Actually, this sigma n, we can see that this is the connection here. With every connection we take here, we take any possible combination of directions, any possible weights that we can have, and these underlying quasi-parabolic bundles are not semi-stable for any weights, any choice of directions, any choice of underlying quasi-parabolic bundle, and any choice of weights. Here I actually put wrong here. Here we are considering just the weights on the image of that maps psi I that do not cover the whole set of weights. But these connections are not semi-stable for any weights. These are very awkward picture. See, but as rather special as it is, we can describe the connections. This up-to isomorphism of the vector bundle, we see that we have a special configuration of directions. The n-1 directions lie on this subline bundle, and the other lie outside this line bundle and this other line bundle. Actually, we can prove that upper isomorphism, this configuration is unique. We can upper isomorphism, we can say that this direction P1 plus is the direction that given by the vector 1, 1 in this in some coordinates for this fiber. And as soon as we fix this direction as 1, 1, all the other directions are determined. And this is a very, very precise, we have a very precise description of these directions. So we have a bunch of a bunch of connections, since all the directions of the directions are given, but the eigenvalues are given. So we can take the difference between two connections here. The difference will give you a Higgs field, but not any Higgs field. Where, since this configuration is very well established, this difference will be a regular as well, a regular Higgs field, a holomorphic Higgs field. So we can parameterize this space by Higgs fields, and as well as we have fixed L. Right? So we have that L is a square root of some line bundle. Then we have 4 copies. The 4 possibilities of L. You have, say, 4 components for sigma n that are described by Higgs fields. So to conclude, outside that sigma n, we have that union of spaces that each one is isomorphic to Sn. And I have to say at least some word about the gluing map. And the gluing map comes from this diagram. We have one side we have the intersection between two of these spaces. Well, the one is that one for the first chamber. We have this intersection, and it's contained in here. I forgot to write this part, the empty epsilon, and we have the inclusions here, of course, and here we have the projection that takes the epsilon directions. We have the isomorphisms to P1 to the nth power. Here we have the isomorphisms that gives all the directions. Here the projection is to the one that makes this diagram, this part of the diagram commute. The other side, we have that same picture. We project to the directions epsilon. We follow this in this space. We take elementary transformation. We go to this space, and we go to the P1 to the nth power. We have the corresponding maps upstairs. Everything here commutes, and we have a map from here to here that's bidirectional. And I claim this here, and then for some who is interested, I invite you to read the proof on the paper. That it's a very I think it's a very beautiful argument, but it's very technical. So that the image of these, well, of the complement here, this intersection is here. The complement of this part, it projects downstairs and take the projection to P1 to the nth power. And here in this P1 to the end, this subvariety goes to a divisor that has this special degree. And here we see that the part that mirrors is that part that lies the points over that are indexed by I, and the others don't matter so much. And this varies. Well, actually, this gamma must be some gamma I, and because this depend for each I, we have some gamma that makes this map. Because outside this gamma here in the left side and in the right side, we can see we have that this map psi I epsilon is an isomorphism, maybe over this set. So that's it that I have to tell you today. So I'm looking forward to tell some other stuff some other day. I think that it's time. So thank you.
Okay, are there some questions or comments?
I have a question, Alan. So about this, so I have two questions actually. So the sigma n, when n is, so you said it's empty when n is even.
Yeah.
So what about when it is odd? Is it, do you know the dimension or the structure of this set?
Yeah, I know that the dimension. I wrote that down the paper, but I forgot it. It's say half the dimension of the space.
Okay.
So not half. It's the whole space has dimension 2n, and this the sigma has dimension n plus 1, if I'm not getting that wrong. It's just we have four components. We said the correspond to torsion line bundles on the curve, and for each component we have one connection for one Higgs field, and the space of Higgs fields has dimension n plus 1. So that just hand wave a bit. It's the dimension count is.
But it's a small set anyway.
Yeah, it's very small.
Okay. And the other question is in what about the space of connections? Is the whole space, is it projective or is it definitely not projective?
Definitely not projective. It's
and is there a natural way to compactify it? Some modular compactification?
There are some ways to consider a compactification. In the paper, we consider just we take, say, that first part, that first chamber, that all the underlying vector bundles are E1, and take the let's say take the lambda connections, that's some generalized object that we somehow say put some Higgs fields on the boundary. So it's these these spaces, we can say that's birational to P1 cross P1 2m times. But there are other objects that we can consider. We can consider some called the phi connections, that the connection does not, they take a section in one vector bundle, but does not spit out the form with values in the same vector bundle. It takes a, it gives you a form with values in some other vector bundle. You have to see when these vector bundles are isomorphic or not. So it gives you some space to wiggle these objects.
Mm-hmm. Thank you.
Any other question?
I have a question, sir. So, Alan, you can also, out of these connections, you can also consider representations of the fundamental group.
Yeah.
Yeah. Did you look at that as well?
Actually, no. For the time being, though. But it's very rather known in some cases. We have the Riemann-Hilbert correspondence, and this moduli space, this whole moduli space. Actually, we are also answering adding to the answer to Carolina. We have this space must be Stein variety. So it's quasi-projective Stein in the sense that the Riemann-Hilbert corresponds must be an isomorphism between this whole moduli space of connections and some affine variety, but this isomorphism is only analytic, it's not algebraic. So it's quasi-projective Stein, but not affine. It's one motivation to study these spaces, to see if this holds, and to give some more examples of these Stein varieties that are not affine.
Thank you, Alan.
Any other question or comments? So let's think again, Alan.
Thank you.